All right, hello everyone, and welcome to lesson 3.8 of the AP Chemistry curriculum. Today we are focusing on representing solutions in particulate models. In the curriculum guide, AP Chemistry clearly states that colligative properties, calculations of molality, percent by mass, and percent by volume for solutions will not be assessed on the AP Chemistry exam. So acids and bases have their own unit later on in the year. However, in order to fully understand all the types of problems given to us for 3.8, I do need to give you a brief introduction of acids and bases and how they look when dissolved in water. So acids and bases are electrolytes that break apart in water to form ions. So an acid is going to donate a proton or an H plus ion, and a base is going to accept a proton or an H plus ion. So for example, HCl or hydrochloric acid, when dissolved in water, is going to produce H plus ions and Cl minus ions. Sodium hydroxide, which is a strong base, is going to dissociate into Na plus ions and OH minus ions. And then we also have our neutral soluble salts like sodium chloride that when dissolved in water, they are also going to dissociate into their individual ions, in this case, Na plus and Cl minus. So the reason we need to know whether an acid or a base is strong or weak is because it's going to look different on a particulate diagram. So when you have a strong acid or a strong base and you dissolve it in water, all of the ions are going to dissociate. When you have a weak acid or a weak base, they are only going to partially dissociate. So it's important to know which acids are strong and which bases are strong. Now for AP Chemistry, you have to know the 7 strong acids and the 8 strong bases, and then you can assume everything else is weak. So these are very important to memorize. I like to use the periodic table just because I'm hoping that when students see the periodic table on their actual test, they can derive some of these acids and bases. Starting out with the acids, 3 of them are directly from the periodic table. We have chlorine, bromine, and iodine. Remember from our last slide, acids donate protons, so most likely they're going to have a hydrogen in front of them. So we have HCl, HBr, and HI. So that's hydrochloric acid, hydrobromic acid, and hydroiodic acid. The other 4 strong acids are with polyatomic ions, and I've created a little jingle to help us remember, and that is clo, no, so, 3, 4, 3, 4. So clo, no, so, 3, 4, 3, 4, and then you have to add your hydrogens. So we know chlorate is a -1 charge, so we only need 1 hydrogen. Perchlorate is also a -1 charge, so we only need 1 hydrogen. Nitrate is a -1 charge, so we only need 1 hydrogen. And then sulfate is a -2 charge, so we need 2 hydrogens. So those are our 7 strong acids, and now let's look at our strong bases. So remember, bases are either proton acceptors or they increase the concentration of OH minus ions in solution. Same thing, but different definition. So our 8 strong bases are going to have hydroxide at the end of their compounds. And to get the metals that are attached to those hydroxides, they actually make a lowercase b on the periodic table. So it starts at lithium, goes down to cesium, goes over to barium and calcium, and it makes a B. And then you're just going to tag on your hydroxide at the end. So your group 1 metals obviously only form a +1 charge, so they only need 1 hydroxide attached. But our group 2 elements have a +2 charge, so we need 2 hydroxides attached. So all of our group 1 strong bases will end in OH, and all of our group 2 strong bases will end in 2 OHs. And those are your 7 strong acids and your 8 strong bases. So when water is the solvent, it's called an aqueous solution, which is also denoted by an AQ next to it in a chemical reaction. If the substance dissolves and produces ions, it's called an electrolyte. Strong electrolytes like sodium chloride or hydrochloric acid completely break into ions, whereas weak electrolytes like acetic acid only partly break apart. Non-electrolytes like sugar or oil don't make any ions at all. They just dissolve as whole molecules. And the key difference between whether ions are present is whether it can conduct electricity. So our electrolytes can conduct electricity, our non-electrolytes cannot. So as mentioned on the last slide, electrolytes are substances that produce ions in water, which means they can conduct electricity. Strong electrolytes like NaCl are going to break apart completely, so they carry current very well, whereas weak electrolytes only partially break into ions, so they still can conduct electricity, but it's much less of a current. And then the strength is going to depend on how much the substance dissociates into ions. Now, what makes an electrolyte strong? Strong electrolytes are substances that completely break apart into ions when dissolved in water. This makes them excellent conductors of electricity. So strong electrolytes include soluble salts, strong acids, and strong bases. And the key idea is that strong means complete dissociation. So for example, hydrochloric acid or hydrobromic acid splits entirely into H plus ions and Cl minus ions, or Br minus ions if we're talking about HBr. The acids and bases in the table are the ones that we talked about on the periodic table 3 slides back. Those are the ones that need to be memorized for the AP chemistry exam, and you can assume all other acids and bases are weak. And then, of course, weak electrolytes, they are weak because there are only some ions in solution, so they do conduct electricity, but not as well as strong electrolytes. The key difference between all of these is that if it's labeled as strong, it means it's 100% ions. If it's labeled as weak, it means that there are some ions, and if it's a non-electrolyte, there are no ions. So let's finally get into what this lesson is all about, which is representing solutions as particle diagrams. So here we have strong acids and weak acids. So let's pretend we're talking about HCl on the left and HF on the right. So HCl is a strong acid, which means it completely dissociates into ions. As you can see, there are no HCl molecules left in this solution. They are all separated into ions. Whereas on the right, we have hydrofluoric acid, which is a weak acid and only partially dissociates. You can see the majority of the molecules are still together, and some of them have dissociated into ions. So we only have 1, 2, 3 F minus ions, and we only have 1, 2, 3 H plus ions, where all the rest of them are still connected via a covalent bond. This diagram shows the difference between ionic compounds and covalent compounds in water. On the left, sodium chloride breaks apart into separate ions, Na plus and Cl minus ions. Since ions are present, the solution conducts electricity, which makes salt a strong electrolyte. On the right, sugar, which is a covalent compound, dissolves, but the molecules stay intact. There are no ions, just whole sugar molecules floating around. And because there are no ions, sugar is a non-electrolyte and cannot conduct electricity. So now let's go through some past AP style questions so that we can get an understanding on how particle diagrams are assessed on the test. This one says HCl is a molecular gas as a pure substance, but acts as an acid in aqueous solution. When HCl ionizes in aqueous solution, Cl minus ions are formed. In the following box, draw 3 water molecules with proper orientation around the chlorine ion. use this specific diagram to represent water molecules. So water molecules are polar, which means they have a partial positive and a partial negative end. The larger open circle is going to represent the oxygen, while the two small closed circles are going to represent the hydrogen. Now, when we're looking at the periodic table, we know that oxygen is much more electronegative than hydrogen is. So oxygen is going to have our partial negative charge, while hydrogen is going to have our partial positive charge. So because chlorine is negatively charged, the positive end of the water molecules are going to face the chlorine ion. So it wants you to draw 3 water molecules looking something like this. And that would be your mark for this question. All right, this next question says ions in a certain volume of 0.2 molar sodium chloride are represented in the box above on the left. In the box above on the right, draw a particulate diagram that represents the ions in the same volume of 0.1 molar calcium chloride. Now, I know molarity is equal to moles over volume. So since the volume is the same in both of these containers, I know that if I am reducing the concentration by 2 or by half, I'm also doing the same with my moles. So on the left here, I have 8 sodium ions and 8 chlorine ions, which means I have a total of 8 sodium chlorides. Now, if I want to reduce my concentration by half, that means I'm going to have 4 calcium chloride ions. And the only reason we can do it this way is because we know they are of the same volume. So because I have 4 calcium chloride ions, I'm going to need 4 calcium ions and 8 chlorine ions because I have 2 chlorines per 1 calcium. So your particle diagram should look something like this. In the space provided below, show the interactions of the components of LiCl by making a drawing that represents the different particles present in solution. Base the particles in your drawing on the particles shown in the representations to the right. Include only 1 formula unit of LiCl and no more than 10 molecules of water. Your drawing must include identity of the ions and arrangement and proper orientation of the particles in solution. So I know I have 1 formula unit of LiCl, which means when dissolved, I have 1 lithium plus ion and I have 1 chlorine minus ion. Now it wants me to draw no more than 10 molecules of water. I think 3 molecules of water on each ion is sufficient to answer the question. So because oxygen is more electronegative, that is my partial negative end, and my hydrogens will assume the partial positive end of the dipole. So with lithium, since it's positive, the oxygen will be closer to the lithium ion. So I'm just going to draw 3 of those to get my point across. If you want to draw 5 because it said no more than 10, you can totally do that. And then with the chlorine ion, I want the hydrogens facing the ion because it's negative and the hydrogen end is positive. So opposites attract. And that would give you your marks on this question. Strontium hydroxide dissolves in water according to the following equation. A student draws the particulate diagram shown to represent the ions present in aqueous solution of strontium hydroxide. Identify the error in the student's drawing. So the first thing when I'm looking at acids and bases, that I want to make sure that it is showing whether it's fully dissociated or only partially dissociated. Now I know strontium hydroxide is one of my strong acids, which means when I see a particle diagram of strontium hydroxide, I should see fully dissociated ions, which I do here. Now, moving on from that, I see there are 1, 2, 3, 4 strontium ions and 1, 2, 3, 4 hydroxide ions, which is a 1-to-1 ratio. And I know for every 1 strontium, I need 2 hydroxides. So that is what's wrong with this particulate diagram, is it's missing 4 hydroxide ions. An ionic crystal is added to water and starts to dissolve as shown in the particulate representation above. Based on the orientation of the water molecules, what can be assumed about the charge of the hydrated particle indicated by the arrow? So we can see the oxygen part of the water molecules are attracted to the ion, which is telling us since the negative end of the dipole is attracted to it, we know that this ion is positive. The diagram shown represents water molecules as they interact with the 2 ions X and Y in solution. Which of the following best identifies ions X and Y? So starting off with X, I know the oxygen, which is partially negative, is attracted to X, which means this is a positive ion. So that only leaves us with A or D. And then with Y, we have the partial positive end attracted to it, which means Y is negative. So our answer here would be A. The diagram above represents aqueous solutions of compound X at various molarities. Each dot represents 1 mole of the solute, and the volume of solution in the large boxes is twice the volume in the small boxes. Which solution has the highest molarity? So we know molarity is concentration or moles per unit volume. And we can see in A, we have 3 over, let's call it 1 liter. So that's going to give us a concentration of 3. Here we have 4 moles over 1 liter, which is going to give us a concentration of 4. And here we have 2 volumes, and 1, 2, 3, 4, 5, 6. So we have 6 over 2, which means this is also 3 molar. And then over here we have 1, 2, 3, 4, 5 over 2 volumes, which is going to be 2.5 molar. So we know our highest concentration is going to be B. And for our last question of 3.8, it says the diagram above represents a solution of ions in water. Which of the following are most likely the identities of ions X and Y? Again, we have the partial positive end of water attracting to X, which means this is a negative ion, and we have the partial negative end of oxygen attracted to Y, which means this is a positive ion. I hope this helped. If you have any questions, please feel free to reach out. I'm happy to help. Have a great day. Bye.